All right, last video in lesson 16. So let's review some terminology. Been looking at hypothesis testing. You should be able to fill in this first one, no problem. The smaller your p-value, the more evidence that there is in favor of the alternative hypothesis. That p-value, it's a probability. It's a conditional probability. It's the probability that we drew our sample if the null hypothesis is true. So assuming the null hypothesis is true, how likely are you to get that sample? So it's a conditional probability. All right, next, data. If we end up rejecting the null hypothesis, we say that the data are statistically significant. That means that the data we collected were very unlikely under the assumption that the null hypothesis is true. So we would say the data are statistically significant. Next bullet. The data are blank if we actually take action based on our hypothesis test. This isn't statistically significant, this is practically significant. Let me explain the difference briefly. Just because you found a statistically significant difference doesn't mean that you would do anything about it. When we looked at that rash ointment, if we found that the new rash ointment was going to be better than the old one, just because statistically that's what we find, if we don't actually take the new ointment to market, then the results are not practically significant. Perhaps it's too expensive to do that. So you do not need to reject the null hypothesis to take action, and just because you rejected the null hypothesis, you do not need to take action. The two aren't the same. Just because the data show a statistically significant difference doesn't mean that that will always lead to action. So only when things lead to action are your results practically significant. All right. Next one here. Okay, we talked a bit about fixed alpha level testing. So don't rely too heavily on fixed alpha level testing. If you think about a problem, if your p-value is 0.049 versus 0.051, and you are doing this at a 5% level of significance, in one case your p-value is smaller than alpha, you'd reject the null hypothesis. In the other case, your p-value is bigger than alpha, you fail to reject the null hypothesis. You'd be making vastly different conclusions, all because that p-value was, hardly changed there at all. So the difference between those p-values results from a tiny, tiny change in your sample data, but you would be making, completely different conclusions here if we just stuck with that fixed level alpha testing. So really think about what the p-value is telling you and don't get too caught up in that fixed level alpha testing. Really think about interpreting that p-value. Okay, what is it when you reject the null hypothesis, but the null hypothesis is true? Type 1 error, all right? And if we run a fixed alpha level test, when we specify alpha, we're actually predetermining the likelihood of a type 1 error. So this is the probability of making a type 1 error that we're comfortable living with when we set alpha. If we're comfortable rejecting the null hypothesis when it's true 5% of the time, that would be a fixed level alpha test with alpha equal to 0.05. So alpha is that likelihood of a type 1 error that you are comfortable with. If we run a test without a fixed level alpha and we reject the null hypothesis, then the probability of making a type 1 error is that p-value. So this will give us how likely were we to reject the null hypothesis when it's true. And if it's small, then clearly you know the likelihood of a type 1 error is small. All right. Therefore, the smaller the p-value, the less likely we are in making an error when we reject the null hypothesis. Some other things. If the consequences of a type 1 error are severe, then you want to pick a small alpha value. Or you want to require a very small p-value if you don't have a fixed level alpha test. So if the consequences of making that kind of error are small, make the likelihood of it small. That's type 1 error. Let's talk for a second about the other one. If you fail to reject the null hypothesis, but the null hypothesis was false, that's a type 2 error. And I don't think we've talked about this yet, but the probability of that happening, the probability of a type 2 error, we can call beta. This is another Greek letter, so it looks like this. And this one's a bit harder to calculate because the alternative hypothesis represents a multitude of values. But we did mention in a previous lesson that the reason why you can't make them both super small is because as the likelihood of a type 1 error increases, the likelihood of a type 2 error decreases, and vice versa. They're sort of inversely related. The only way to reduce the chance of making both types of errors, there was one way, and that was to collect more data. Which is great in theory, but practically, collecting more data is definitely going to cost you money and take you more time. But that is the one way you can reduce the likelihood of both of those errors at the same time. All right, let's wrap up this lesson with a couple of examples. So testing for lupus is difficult because the signs and symptoms vary considerably from person to person. So recently, a few medical interns created a quick screening test. A patient who tested positive would then be referred to a rheumatologist. The interns believe that there is a false positive rate with their quick screen of 3%, and we presume there's a false negative rate of 8%. All right, part A. What will we assume about every patient before going through the initial screening? So before they go through, we're going to make the assumption that the patient is healthy until we find evidence that the patient's sick. So we will assume the patient is healthy. Until symptoms convince the doctor that the patient is sick. You go to your doctor, they need to see some symptoms before they're going to give you something for what they think ails you here. So in words, what are our two hypotheses? If we look at this as a hypothesis test. Remember, the null hypothesis is what you assume to be true, and the alternative is what we're looking for evidence of. So we're going to assume that the patient's healthy. And for this particular problem, we're looking for evidence that the patient has lupus. So here are our hypotheses. All right, and then from here, we're going to go on in C and D and talk about what would committing a type 1 error be and what would committing a type 2 error be. So, okay, in words, explain what happens if we make a type 1 error. So remember, a type 1 error means we reject the null hypothesis. We would conclude the patient has lupus when the null hypothesis was true, when the patient was actually healthy. So just in general, this is when you reject the null hypothesis, when it's true. in the words of this problem, you know, we'd be concluding the patient has lupus, sending them on for a more extensive round of tests when they were actually healthy. So you know what's bad here? A healthy patient gets sent for more extensive tests here. Sent to a rheumatologist and further investigated there. So that would be a type 1 error. Part D is going to be what happens if we make a type 2 error. What happens if we make a type 2 error? A type 2 error happens when you fail to reject the null hypothesis. So we keep this, when in fact the alternative is true. All right, what's that mean for this one? If we fail to reject the null hypothesis, we're concluding patient's okay, patient's healthy, when in fact the patient has lupus. So this is pretty bad. Oh, I forgot to talk about the errors. I'll add that here. This is definitely worse than a type 1 error. You know, now you're telling the patient, hey, go home, you're healthy, when they actually have lupus here. So we conclude the patient's healthy. When they actually have lupus. Yeah, you just sent a patient home thinking that they're now, you're telling them they're healthy when they're really sick here. Okay, I'll do this with this one, and then you'll have to flip back to C and make an adjustment on this too. I had forgotten that we were told the likelihood with this test of a false positive or a false negative. So in this case, a type 2 error. A type 2 error is a false negative. Here, you're told, nope, your test for lupus came back negative, you're healthy, when really that's not true, that's false. So the likelihood of this happening, I hope, was 8%. So this is a false negative. And the chance of this happening is 8%.
Might be different on the slide.
Darn.
Oh well.
Hold on, let me go back and read.
Yep.
No, I got that right.
Yep.
8 and 3.
All right.
I wrote them down.
Sorry.
No, that's okay. I thought I did, but just. I'm glad I checked though. That makes me feel better. It has an 8% chance. Okay, now I'm not going to erase all this and go back, but you look back up at part C, and I'm going to have you add one thing to that. Remember, part C was a type 1 error. A type 1 error was rejecting the null hypothesis, but it was actually true. In that case, that's a false positive. The test comes back that oh, I can't do this without seeing it. I got this one up here. We concluded in that one that the patient has lupus when they actually don't. So we conclude, hey, the test comes back positive, you have lupus, but that was false, that wasn't true. So you have that written back in part C. The only thing I want to add to that is that's a false positive. And the likelihood of that happening, there's a 3% chance. So just back in part C, add that this was a false positive. We falsely concluded you had lupus, and the chance of that happening was 3%. So that was the only part I left off of there that I wanted to include. All right, let's go to a new one. Last one. Gallup reported in November 2013 that 16.6% of all adult Americans are underemployed. This was based on a sample of 2,500 people. So in March of 2011, the figure stood at a flat 20%. A test was run to determine if this was a statistically significant decline, and the p-value was 0.00001, 4 zeros and a 1. Not sure if I said too many. Clearly, the researchers concluded there was a decline. That p-value is extremely small. Interpret the p-value in the context of this problem. All right. So in 2011, the percentage that were unemployed was 20%. Now we've moved on to November of 2013. We look at a sample of 2,500 people, and the percentage that are underemployed is now 16.6%. We were trying to see if that was a significant enough drop there. Based on our test, we got this incredibly small p-value, so we concluded that there was a decline. Interpreting that p-value, if it really is still 20% are underemployed, how likely would you be to get a sample of 2,500 people where 16.6% of them are underemployed? You could get that kind of thing to happen, but how likely is that to happen? And that's what the p-value is. So let's just write this up in the context of the problem. If 20% of people are still underemployed, assuming that null hypothesis is true, we would get a sample like ours. And in the sample, it was what, 16.6% were underemployed? We'd get a sample with 16.6% underemployed. Or one even maybe with fewer people underemployed. So maybe even a sample more extreme. That would happen with a probability of 0.00001. If I convert that to a percentage, I'm going to have 0.001. We get a sample with a likelihood or with a probability. How often are we going to get a sample like ours? We're going to get a sample like ours, or one even more extreme, 0.001% of the time. Since that was so incredibly unusual, that led us to believe that, hey, we don't believe this initial assumption here that 20% are still underemployed. So because that was so unusual, the data convinced us that the percentage has declined from that 20% or decreased from that 20%. You should definitely know what a p-value means by now. So it is the probability or the likelihood of you getting your kind of sample data or sample data even more extreme under the assumption that the null hypothesis is true. And so that's where we try to put into words with this one, but in the context of a problem. All right, finally, lesson 16, hypothesis testing for proportions. We are done. So we'll see you in class. Thanks.